Our very next topic is dynamic routing. And there's one point that I do want to make here. I want to take that time, advantage of the introduction of this topic and share a point with you guys. When it comes to technology, when it comes to our industry, there's a collection of features, and oftentimes we wonder, how can we keep that, and why not use this one, and why not use, static routing versus dynamic routing, OSPE versus RIP. And you got to realize, and you got to always remember this. Whenever we study technology, whenever we study IT, you really need to be mindful of the history. So if this is a time line going that direction, this is feature set. So when you look at this, that will be the historical time in terms of features in the technology industry. Well, in the 90s, early 90s, and late 80s, the very first thing that we could do was just simply static routing. And as we start moving along here, the need for dynamic routing, basically, I need the routers to find themselves and become neighbors to each other and exchange table. And the major need that drove that was the fact that static routes was very difficult to manage. Once you get past 5, 10 or 5 routers, it just became cumbersome to manage the routing table. So somewhere along the line, we started doing dynamic routing. And the very first version of that was RIP, or Router Information Protocol. And as soon as we finished that, we found it was very nice. It worked out pretty nice, but we found that we could actually do a lot better. So not too long after that, and there were some specific complaints about this feature, and we'll talk about it. We came along with a new set of requirements for dynamic routing protocol, which today we know, the end of which we know today as OSPF. So we will talk about dynamic routing. We're going to talk specifically about two of them, the two standards, but I want you to be very mindful of this time table and understand that it's not that we develop them at the same time. And if you develop them the same day, you're wondering why one versus the other one. It is actually evolution, technology evolution. So the very first question and the very first bullet item here says we need a way to build the tables dynamically. And what that really means is if I have routers all over my network, if I have routers going around, and let's say you have a network of about 50 routers all across the board, you need a way for them to find each other and exchange routing information and build a cohesive routed map or map on how to get from one network to another network across the board that is stable. Otherwise, it becomes very difficult to manage this on your own. You also need to know if this guy fails right here from this router, I can get to, and let's just call this router A, this router B. So from A, I can get to B. I could reroute my traffic that direction and then here or in that direction and go around. If you were to do this, if you were to have a static table and this fell, this guy right here will never know. And he will never change his routes. So that's the main reason. That was one of the biggest push. So routers need to find each other. They need to, whether it's broadcast, advertisement, they need to go out in the network and say, I'm a router. And as soon as somebody else say, oh, by the way, I'm a router too, they should be able to have some sort of handshake, if they belong to the same club, some sort of handshake, identify each other, and exchange information in terms of routing tables. And dynamically build the routing table instead of manually. They need to send each other their routing information so they can build it dynamically. And then they will need to send updates. So as the network morph and change and you add routes, there's no need for you to tell everybody else. They should dynamically learn. They need to let each other know about updates of your network, as well as failure. The network is a living thing. And it's constantly changing. So these were the basic requirement that developers found themselves right before they built the first dynamic routing protocol, which we know as RIP. Very good. Let's move on to the next slide. RIP, or Routing Information Protocol, was our very first attempt to develop a dynamic routing protocol. And let's just draw here so you get an idea on how this thing worked. Very good. Let's just say this is router 1, router 2, router 3, router 4. And you have, I'm going to build you a network right here. I'm going to say this particular connection here is going to be 64K. This particular connection here is going to be 1 meg. 1 meg. There's a specific reason why I'm doing this, so just bear with me. So RIP, as soon as you turn on the RIP process on the router, it will advertise across every single connection that I am a RIP router. If it turns out the other side along that connection is a RIP router, they will start exchanging routing information. In fact, RIP will do it every X amount of minutes. This you could configure, you can adjust, but the default, if I remember, was somewhere around something like every 30 seconds, right? And it will send the full table, all the table, 100% of the table. So we figured out how to find each other by advertising in every direction. I happen to be a router. The other guy will say, well, I'm a router too. And then we start exchanging tables across the board. So what really happened is whichever network was attached to RIP, he'll have a little table. He'll share that with this guy. And whichever table was network was attached to router 2, he put that on his table and he shared that with that guy. As soon as router 1 gets router 2 table, it will update. Router 1 will update his table, which now it will include my attached network plus whatever new information I got from router 2. And that went along and propagated and went along until everybody knew how to get to every network. That worked out pretty good at the very beginning. And for it to be our first generation dynamic protocol, that was pretty clever. A couple of things happened after that. The first thing that happened is router 1, 30 seconds after he got router 2 table, it will compile a table and send the full table back to router 2, even though router 2 is fully aware of the information. So regardless of any change of the network, they will send full table constantly. And that's going to eat up bandwidth. That's going to cost bandwidth every time you send a full table. So one of the small requirement, one of the requirement that made it to the wish list for the next generation was, hey, is there any way after I finish exchanging my information, don't send me the table. You're consuming bandwidth and processing power. Just, send a keep alive packet, a little ping, something that says, router 2, are you still alive? Yeah, I'm here. Good. Now, if you notice a change, do let me know and send me that information, and then I will recalculate. That was one of the little features that made it to the wish list for the next generation. The other thing that became pretty interesting on RIP was how it calculates its route. RIP was very unique about that. So let's take a look at this. The algorithm, which is really not a very complex, for RIP to calculate a route was based on hop counts. So as it builds the table, so here's my routing table, and let's just say I have LAN here, LAN 2, and right here I have LAN 1. Okay, let's just say that. If I wanted to go from LAN 1 to LAN 2, I'd take a look at I will take a look at my actual little table, and then I will realize that if I wanted to go this way, if I wanted to use the 64K connection, it will be only one hop. But if I wanted, in fact, to use my 1 gig connection, which is a loss factor, it will take 2 hops. RIP will always use the smallest amount of hops. So if it turns out that you have a file that is 1 gig big, 1 gig size. And if you take a look at that diagram that I showed you there, clearly going through the whichever 1 gig connection, it'll be a lot faster based on the bandwidth. RIP did not care. The only metric it used to make decision was number of hops. So it doesn't take a genius to realize that that is a very, very unreliable or unproductive way to make routing. So again, keep in mind that the main reason we did this is based on generational. So we did at that point decided that maybe we should figure out a better way to route this. And then from RIP, we went to our next generation routing protocol, dynamic routing protocol, which happens to be OSPF. Very good. So now the other thing that RIP will provide for you is what we call routing loops. And routing loops become interesting. And let me draw you that. So let's just talk about this table, routing table for this guy, and this routing table for this guy. Now, this router here sent all the information to this guy, and including networks. Let's say this is LAN 3 and LAN 4, including networks that he learned from this port right here. Now, mind you, this router here also learned about this network through this router. So he will send this guy information and say, hey, by the way, L4, L3, L4, I can find them from this router. So this guy right here is going to say, oh, hold on for a second, and it will update his table and put that information again. And then he'll send it to this guy and say, hey, by the way, I can find this guy here. And then all of a sudden you're going to end up with a loop right there. It's going to drive you crazy. We have two ways to deal with that. One of the things that we have is when this guy sends information, I will rebuild my table. I'm going to keep here the information that is attached to me, the networks that are attached to me. And then I'm going to take all this information, add it to this guy. And then I'm also going to, on the table, I'm going to have here a piece of information that is going to say from which port, meaning this interface, from which physical interface did I learn that route. That way, when I send information that way, I send everything except for whatever I learned from his table. And that's how we keep from creating loops. Very good. Our next one is evolution from RIP to OSPF. OSPF came soon after RIP, mainly based on a couple of issues. Number one was the algorithm used to calculate routes, and number two was the constant updates, force updates, whether there was a change in the network or not, constant table being consuming bandwidth, which it gets to be pretty expensive if you were to calculate that. So the number one, the core requirement behind OSPF was efficiency. We wanted to make sure that instead of sending broadcast messages to introduce a router to another one, we use a multicast IP address, and I'll describe what that looks like logically. But we're going to use a multicast, a well-known multicast IP address, and every single device that does OSPF will subscribe themselves to that IP address, to that multicast IP address, and actually exchange information there. They will have to go through a small process, and it's called the neighborhood process, or the neighboring. The routers will have parameters that they have to exchange before they agree to be neighbors. Once they become neighbors, they would in fact exchange all the topology information required for each one of the router to calculate the full network topology from their point of view. The other thing that they will have will be trigger updates, which means once the topology is converged in all the routers, once every single router has a good vision, a good view of the network topology from their point of view, there is no need to keep exchanging tables. There's a need to make sure the other routers are still alive. So that consumes a lot less bandwidth. And, there's keep alive packets and are you there? Yes, I am here. But there's no need to constantly change the table. So if there was a change of topology, that would trigger an update on everybody's table. And that's what we mean by trigger update. The other thing we did is we created a hierarchical model. And the intention of the hierarchical model is to, number one, make sure there's no routing loops. And number two, if there's a problem on a segment of the network, you could isolate that problem without propagating network topology reconversion and recalculation. And that way you can isolate a problem and not have the whole network collapse, but a section of the network.